Welcome to the Unit 0 Section 4 video on polynomial vocabulary and operations. So we're going to work with polynomials quite a bit in this section, so before we do so, let's get a little bit of the vocabulary under our belt. Now the simplest type of polynomial that you can have is a monomial. And a monomial is a number, a variable, or a product of numbers and variables. So remember, that's the key word, a product. So here's some examples of monomials. We've got -9, we have y, we have 7a, we have 3y cubed, and 1/2 abc to the 5th. Okay? These are all considered monomials because they are a product of variables and numbers. Now in that last one, 1/2 is a number, so that is okay. What is not okay is having more than one term, such as m plus n. That would not be a monomial because it's got more than one term. M is a term and n is a term. We also are not able to have any division by variables because that's not really considered a product. In other words, we can't have something that has a negative exponent. 1 over y is considered to be y to the -1. So since we can't work with negative exponents as part of the product and we can't divide by the variables, then x over y is not a monomial. 3 minus 4ab is not a monomial because again it's got two terms. 3 is a term and -4ab is a term. We have 1 over x squared. That is not a monomial because again you cannot divide by the variables. And the same goes for 7y over 9z. That also is not a monomial. Okay, so let's say we've got monomials that are added together. Well, then we'd have more than one term, and we can generally call them polynomials. Okay, so a polynomial is an expression that can be written as a sum of monomials. It's important to note that a monomial is a polynomial. It's just a polynomial with one term. And again, it has a positive exponent. A binomial is the sum of two monomials, and a trinomial is the sum of three monomials. So let's do some examples comparing those. We've got 5x squared, that is a monomial. 4abc would also be a monomial. And -7 is a monomial. Because remember, a number in itself is a monomial. Well, here are some examples of binomials. 3x is one term, and then we add it to a second term, which would be +2. That gives us two terms and a binomial. Here's another one that has two terms, 4x plus 5y. And we not only can add, but we can also subtract and end up with two terms, and that gives us a binomial. And then a trinomial, as you would expect, has three terms. Okay, so we've got 5x squared minus 2x plus 7. That is a trinomial, and you may recognize that as a quadratic. We have a squared plus 2ab plus b squared, and that is a trinomial. In fact, that's not just a trinomial, it's a perfect square trinomial, which we'll be talking about more a little bit later in this video. And then finally, here's one more example of a trinomial, 4a plus 2b squared. And we need one more term, so minus 3c. Now that we know what polynomials are and what monomials and binomials and trinomials are, let's talk about how we can classify these a little bit. So let's classify it by a term called the degree. Okay? So the degree of a monomial is the sum of the exponents of its variables. Okay, so in this first one, we only have one exponent in one variable. That's 2, so our degree would be 2. In the second example, we have three variables, a, b, and c. This a is raised to the first power, even though it's not written there, it's understood to be there. So we got a to the 1, b to the third, c to the fourth. So if we add those exponents together, that would give us the degree of that monomial, which would be 8. Now if we have just a number, there's no variables, so there's no powers happening, so the degree of this would be 0. Now, those are the degrees of monomials. If we wanted to find the degree of a polynomial, say one that's got more than one term, then the degree of the polynomial is simply the greatest of its terms. Okay, so here's an example that we can kind of look at to see how that works. Let's find the degree of 8x cubed minus 2x squared plus 7. Well, if we want the degree of this, we've got to look at the degree of the terms. So the first term, the degree is 3. The second term, the degree is 2. And the third term, the degree is 0. Well, what is the greatest of these three degrees? It's 3, so therefore our polynomial degree is 3. Now let's talk about adding and subtracting polynomials, because we actually want to work with these things. Well, you can add and subtract polynomials by either grouping like terms together and then finding the sum, or you can write them in column form and find the sum that way. So let's do this first example here, this example 2, and let's start off by grouping the like terms. So when we group the like terms, we're simply going to take anything that's got a y squared in this one, which we've got 3y squared in the first polynomial, and then a 7y squared in the second, and we're just going to put them together. And then we're going to add the next grouping. Well, we've got a 5y, and there's no y's in the other one, so 5y stands alone. And then finally, we've got a negative 6, and we're going to add it to the negative 9 in the second polynomial. Now that we've got everything arranged, we just combine the terms. 3y squared plus 7y squared gives us 10y squared. 5y is by itself, and then negative 6 minus 9 will give us negative 15. So that is our answer, 10y squared plus 5y minus 15. Well, you can also do this in column form by stacking the terms. So you've got 3y squared plus 5y minus 6. And we're just going to take the like terms and stack them underneath. So we've got 7y squared. We're going to put that under the 3y squared. And then we're going to put negative 9 under the negative 6. And then we're going to add these. 3y squared plus 7y squared gives us 10y squared. And then we've got 5y added to nothing, so it's just 5y, and then minus 15. So 2 ways to get to the same answer. Okay, so let's do another example. Let's do one where we're subtracting. So let's find the difference between these two polynomials. Well, let's start off with the first method, where we group like terms. So when we group like terms, we're going to end up with 4x squared. Now, this is where you want to be careful with your signs, because we're subtracting this time around, okay? So our operation, when we group the term from the second polynomial, is going to be subtraction, and we have a 6x squared on the other side of that. Okay, now we're going to add it to our next term. We've got negative 3y squared, and we're subtracting another 3y squared. And then our final term, we've got a 5xy, and we are going to subtract the 8xy in the second polynomial. Now that we have grouped our terms, now we just need to simplify. So 4x squared minus 6x squared. It's going to give us a negative 2x squared. Then we have negative 3y squared minus another 3y squared. That's going to give us a negative 6y squared. And then our last term, 5xy minus 8xy. That's going to give us a negative 3xy. And then we just simplify one more time from there. We're going to distribute our minus signs, and we get our final answer. Similarly to how we did the last example, we can also subtract in column form. So let's line up our like terms. So we'll start off with our first polynomial and write that as is. Now we're going to line up each of our terms in our second polynomial. So the first one is 8xy, so that's going to go under the 5xy. And then we have a 6x squared. Well, that will get placed under the 4x squared. And then we have a 3y, which will get placed under the 3y squared. I should say that's a y squared term. And we're going to subtract. So 4x squared minus 6x squared, that's going to give us negative 2x squared. Minus 3y squared minus 3y squared gives us minus 6y squared. And then 5xy minus 8xy gives us negative 3xy. So again, two ways to get to the same answer. Okay, let's kick it up a notch. Let's apply this to geometry. Okay, we have a triangle here, and we want to find out what the measure of this side with the L on it. We want to find out what this measure of L is, okay? Well, we're given a couple of pieces of information. We're given what the perimeter is. That's over here on the side. And then we're also given what each of these two sides are, what the length are in terms of a polynomial. And we know perimeter is the sum of the measures of the three sides of the triangle. So let's set it up first of all that way, okay? So we know that our perimeter, which is 12x squared minus 7x plus 9, we know that's going to be equal to the sum of the other three of the three sides. So we'll start with the first one, 3x squared plus 2x minus 1. And then we're going to add it to the next side, which is 8x squared minus 8x plus 5. And then we're going to add it to the third side, which is just simply L. Okay, so now that we have set it up, we want to get L by itself. And the way we do that is we're going to subtract the two sides in this polynomial form from each side to get L by itself. So when we do that, we end up with 12x squared minus 7x plus 9. That's our perimeter. And we're going to subtract the other two sides. 3x squared plus 2x minus 1. And 8x squared minus 8x plus 5. And that is equal to our length. So now we've got it in terms of what we're trying to find. Now all we need to do is carry out the subtraction between these polynomials and simplify things down to get what our L is. Well, let's start off by distributing out the minus sign on these two polynomials, okay? So we'll start off by doing 12x squared minus 7x plus 9. Nothing's going to change with that one because there's nothing in front of it. But now we're going to distribute this minus sign. So we end up with minus 3x squared minus 2x plus 1, because a minus and a minus gives you a plus. And then on this last polynomial, we get minus 8x squared plus 8x minus 5. And that's still equal to L. So now the next thing we want to do is gather our like terms. So let's gather together our x squared terms. So we've got 12x squared. And then we also have a minus 3x squared. And we also have a minus 8x squared. Okay. And now let's gather together our x terms. We've got a negative 7x. We've got a negative 2x. And we've got a plus 8x. And then finally, we'll gather together our terms with no variables. So we've got a 9, a 1, and a negative 5. And I think you're going to find very quickly the answer is going to fall out from here, now that we've grouped everything. So 12x squared minus 3x squared, well, that's going to give us 9x squared. 9x squared minus another 8 gives us x squared. Moving on to our x terms, we have negative 7x minus 2x, which is negative 9x. Negative 9x plus 8x gives us negative x. And then finally, 9 plus 1 is 10. 10 minus 5 is 5. And that is our answer for what the length of the third side is. Now let's talk about multiplying polynomials. The big rule that we're going to be using to multiply polynomials will be the distributive property. And that is to multiply a polynomial by a monomial. So we're going to start on the easier side and we're going to work our way up. So first, let's find 5a times this polynomial. Well, to do that, we're simply going to take 5a and multiply it by the first term. And then our operation is addition. And then we have 5a times our second term. So essentially, all I did was I took this 5a, I multiplied it by the first term, 5a, multiply it by the second term. That's all that's happening here. We distributed the 5a amongst the terms inside that polynomial. And then we just simply carry out the operations. 5a times 3a squared is 15a to the third. And then 5a times 4 is 20a. And that's our answer. Let's do a couple of more of these. In example 6, we want to find 2m squared times this polynomial. So again, we're just going to do 2m squared times the first term. Our first operation is subtraction. 2m squared times the second term. The next operation is addition. 2m squared times our last term. And when we do this, we end up with 2m squared times 5m squared, which is 10m to the fourth. And then 2m squared times 7m gives us 14m to the third. And we're subtracting it. And then we have 2m squared times 8. That's 16m squared. And there's our answer for that one. So these problems are fairly quick and easy. Let's do this last example to finish off this little section. So we've got negative 3xy times the first term, 2x squared y. We're adding negative 3xy times the second term, which is 3xy squared. And then we're subtracting a negative 3xy times 7y to the third. It is very important to keep track of what operations are being done and what the signs are on your things. It could be very easy to just do minus 3xy here, but we're subtracting because that's our operation in front of the 7y cubed. And then we have a negative in front of the 3xy. So you have a negative and a negative here, which will end up being positive, but it's important that you don't lose track of what you have so you end up with the correct operation in your final answer. Okay, so the first one, we've got negative 6 x to the third y squared. Okay, so we did our coefficients, gives us negative 6, x times x squared gives us x cubed, y times y gives us y squared. The next one, we end up with negative 3 times 3, which is negative 9, x times x, which is x squared, and y times y squared, which is y cubed. And then in our last term, we have a negative times a negative, so that's going to give us a positive. 3 times 7 is 21. We have an x, and then y times y to the third is y to the fourth. And that is our final answer. Okay, before we move on, let's do an application. Let's go back to geometry. And in this particular geometry problem, we were given two rectangles, one inside the other. And what we want to find is the measure of the shaded area. Now, to find the measure of the shaded area, we're going to take the area of the larger rectangle, and then we're going to subtract the area of the smaller rectangle because that's the part we don't want. And that's going to leave us with the part we do want. Okay, so let's set this up. We're going to take the outside rectangle. That's going to be 2a times this polynomial on the top, 5a squared plus 3a minus 2, because the area of a rectangle is length times width, or you can do width times length. And then we're going to subtract this other rectangle. So we have the area being 8 times 3a squared minus 7a plus 1. So now we're just going to multiply our monomial to our first polynomial, and then our second monomial to our second polynomial. I'm going to go ahead and go to another line here, just so we have the space. So you remember how to do that from just a little while earlier. We have 2a times 5a squared, and then plus 2a times the second term, being 3a, plus 2a times the third term, which is negative 2. Now we have a minus 8. Okay, so we're going to do plus negative 8 times our first term, which is 3a squared, plus negative 8 times our second term, which is negative 7a, and then finally negative 8 times our last term, which is just 1. So now we're just going to multiply each of these. So 2a times 5a squared gives us 10a cubed. Then we have 2a times 3a, that's going to give us 6a squared. Then we have 2 times negative 2, which is negative 4a. And then we have negative 8 times 3a squared, that's going to be minus 24a squared. We have negative 8 times negative 7a, so that's going to be positive 56a. And then finally on the end, minus 8. And now we're just going to combine what like terms we have. Well, there's nothing to go with the 10a cubed, but we do have two a squared terms. That's positive 6 and negative 24. So that's going to end up giving us negative 18a squared. And then we have negative 4a and a 56a. And when you combine those, you end up with plus 52a. And then minus 8 is by itself. And that's our answer. That would be the area of the shaded region. Okay, so now the distributive method can be used for binomials as well. And when we multiply two binomials, there's actually a mnemonic device that we can use to help us make sure that we get everything that we're supposed to get and we don't repeat doing the same thing twice. Because when you have two things, two terms multiplied by two terms, things can get a little mixed up. So this is just to help us make sure we're not losing anything along the way. Okay, so this is the FOIL method. For multiplying two binomials. Okay, so here below is how it works. We have two binomials, 2x plus 3 and 5x plus 8, and we're multiplying them together. So what we're going to do is we're going to take our first terms and we're going to multiply those together. So that's 2x and 5x. Then we're going to take our outside terms, 2x and 8, and multiply those together. We're going to take our inside terms, 3 and 5x, and multiply those together. And then finally our last terms, 3 and 8, and multiply those together. And everything that we multiplied together, we're going to add up. So our 2x and 5x give us 10x squared, 2x times 8 gives us 16x, 3 times 5x gives us 15x, and 3 times 8 gives us 24. And then the last thing we're going to do is just combine those two x terms to give us 31. And that would give us our answer. So we're doing the first terms plus the outer terms plus the inner terms plus the last terms, and that gives us FOIL. That gives us the word FOIL if you take the first letter of first, outer, inner, last. Again, all it is a mnemonic device to help you keep track of what's happening. You can do these things in any order that you would like, but this is just to help you keep track of what you've done and what you haven't done, so you don't repeat anything and you don't miss anything. So let's do a couple of examples of this. Let's find y plus 5 times y plus 7. Okay, so when we do this, we're going to do our first terms, y times y, plus our outside terms, y times 7, plus our inside terms, y times 5, plus our last terms, 5 times 7. And what we end up getting is y squared plus 7y plus 5y plus 35. And we can combine our y terms, and that gives us y squared plus 12y plus 35. All right, let's do one more example of this. This is a fairly straightforward method. All right, our first terms, 3x times 5x, plus our outside terms, 3x times 2, plus our inside terms, that's negative 5 times 5x, and then our last terms, which would be negative 5 times 2. Now let's just multiply things. We've got 15x squared plus 6x minus 25x minus 10. And then the last thing to do is just combine our x terms that are on in the middle of this. And that gives us negative 19x. And we have our final answer. Okay, so FOIL works well when we're multiplying two binomials, but it doesn't work as well when we're trying to do more than that, because now we can't do first outer, inner, last because there's an extra term. Like in example 11, we now have 3 terms in the second polynomial. So we go back to our tried and true distributive method. So we are going to do our first term, 2x, times each of our terms in our second polynomial. So we've got 3x squared minus 5x plus 4. And then we're going to have minus 5 times our second polynomial. And now we're just going to distribute the monomial term to each of our polynomials. So this gives us 6x cubed minus 10x squared plus 8x. Now here we have 2 options. We can go ahead and just do minus and distribute the 5 and just put a minus in front of it and put a parentheses around everything, but let's skip that step and just do minus 5 out to everything. So if we do that, we end up with negative 15x squared, and then minus 5 times minus 5 gives us plus 25x, and then we end up with minus 20 on the end. Now we're just going to combine our like terms. So 6x to the third is by itself. Then we have a minus 10x squared and a minus 15x squared, which gives us negative 25x squared. And we have 8x plus 25x, that gives us 33x. And then minus 20 on the end. And that's our answer. Let's go down to the second one here. Now we've got a trinomial times a trinomial. Well, it's going to be handled very much the same way as we did in the last example. We're just going to have one more set to work with, and you'll see what I mean here in a moment. So let's start with x squared. I'm going to multiply that by our second polynomial. Then we have minus 5x, and that's going to get multiplied by the second polynomial. If I can write it correctly. Plus x minus 7. There we go. And now let's do plus 4 as our third term. So you'll see that we have one more set of a monomial times a polynomial to take care of. All right, so now let's multiply these out. We're going to end up with 2x to the fourth plus x to the third minus 7x squared. That takes care of our first one. Now our next one, we end up with minus 10x to the third minus 5x squared plus 35x. And then the last one, we're going to have 8x squared plus 4x minus 28. Now you'll notice that we have a lot of terms that we need to group together. So here is something that I suggest as we go through and group these. First of all, the x to the fourth term stands by itself. There's nothing else to group it with. As you use terms and group things, I would highly encourage marking them off so that you don't double up anything and that you don't forget anything. So let's look at our x to the third terms. We got x to the third minus 10x to the third, and that's it. Those are the only two x to the third terms. So that's going to end up giving us minus 9x to the third. So we've used those, so we're going to cross those off. Now we're going to go to this x squared terms. We've got negative 7x squared, negative 5x squared, and a plus 8x squared. So when you put all those together, you're going to end up with negative 4x squared. Now we'll cross those off. And now we have two x terms, 35 and 4. So that gives us 39x. We'll cross those off. And all that's left is the negative 28. So I'll go ahead and cross that off and add it to the end here. And that would be our answer for the product of those two trinomials. So this next section we're going to talk about is closure of polynomials. And this is going to be a section I'm going to move fairly quickly through because the idea in itself is fairly basic. There's no real math examples to do with this. This is more of a concept that just needs to be shared as part of the content of this course. So we have a set of numbers being considered closed, or we can say that it has closure under a given operation if the result of the operation on any two numbers in the set is also in the set. So, for example, the set of integers is closed under addition because adding two integers results in another integer. Let me give you a quick example of that. So we've got 9 plus 5. Okay? 9 plus 5 equals 14. Well, 14 is also an integer. 9 was an integer, 5 was an integer. We put those two integers together through addition, and we end up with an answer that is an integer. And that's always going to happen. When you put two integers together, what you get out is going to be an integer. So since that's always going to be the case, then we can say that integers are closed under addition. Integers are also closed under subtraction. They're also closed under multiplication. Okay? So we're going to describe polynomials like this. We're going to describe them in terms of their closure. So here's the first rule, that polynomials are closed under addition. And so all this means is that when you add two polynomials together, you're going to get a polynomial as your result. So in this example I give you here, we have 2x squared plus 3x plus 4. And if we add it to another polynomial, x squared minus 5x minus 3, then your resulting polynomial is going to be 3x squared minus 2x plus 1. That result is also a polynomial. So when you add two polynomials together, what you end up getting is a polynomial. So since that's always going to be the case, then we can say that polynomials are closed under addition. The same can be said for subtraction. Okay, so let's take the same example, the same two polynomials, but instead of adding them, let's subtract them this time. And when we do, we're going to end up with x squared plus 8x plus 7. Well, that answer is a polynomial. So since that answer is a polynomial, then we can say that polynomials are closed under subtraction. And not just because this polynomial works that way, but because all polynomials work that way. Okay, so we're moving pretty quickly through this section. I think this section is fairly straightforward. We can say the same for multiplication. When you have closure under multiplication, you multiply two polynomials together, the result is going to be a polynomial. And we've seen that already with some of the things that we have multiplied. Our answers have been polynomials, and this one would be no exception. Now, I'm not going to go through the exercise of actually doing the work on this one. I'm just going to give you what the result is. You can work this one out for yourself if you'd like. But this result, when we multiply the two polynomials, is a polynomial. And that occurs every time you multiply two polynomials together. So therefore, you can say that polynomials are closed under multiplication. Okay, so we found that they're closed under addition, they're closed under subtraction, and they're closed under multiplication. Well, now probably your big question is, how about division? Well, division, as it turns out, is not an operation where polynomials are closed. And here's a simple example to show you that. We have x to the third, which is a polynomial. It's a monomial, but remember, monomials are polynomials themselves. So you got x to the third, and we're going to divide it by x to the fifth. Well, we can use our exponent rules to find that this is x to the 3 minus 5, which would give us x to the negative 2. Well, remember, we cannot have negative exponents for a polynomial. And to kind of just drive this home a little bit further, using the negative exponent rule, this can be rewritten as 1 over x squared. We can't divide by a variable and it be a polynomial. So therefore, since we don't get a polynomial as a result, when we divide two polynomials, then polynomials are not closed under division. All right, now let's move on to factoring. Okay, we're going to start taking those polynomials that we multiplied together and we got the result. Well, now we're going to start with that result and try to get back to polynomials that are broken apart. Okay, so in multiplication, the quantities being multiplied are called factors. Okay, so if you think about a simple multiplication problem like 2 times 3 equals 6, 2 and 3 are factors of 6. Factoring involves breaking an expression down into smaller parts that can be multiplied together. So let's start simple. Let's just start with a number like negative 525. Okay, and let's factor this one down. So we know that this is going to be factored down when we have this written in terms of negative 1 multiplied by some string of prime numbers, because prime numbers cannot be broken down any more than they are. Because remember, a prime number can only be divided by 1 and itself and nothing else. Okay, so the first step is, since it's negative, we're just going to factor out a negative 1. Now we're going to work our way from the bottom up. Okay, well, we're not going to start with 1 every time because every number can be divided by 1. But let's move on to 2. 2 cannot be divided into 525, so now we move on to 3. 3, as it turns out, can be divided into 525, and it's 3 times 175. Okay? So that's our first breakdown. So now we're going to continue our string, and we're going to try to break down 175. Well, we know 2 can't go into it. We know 3 can't go into it again. We don't need to bother with 4, because if 2 can't go into it, we know 4 won't go into it either. And so now we move on to 5. 5, as it turns out, can, and the big giveaway is that it ends in a 5. Okay? And it turns out 5 times 35 is 175. Well, now we're to the point where we know that 35 can be broken down one more time because it's 5 times 7. And 5 and 7 are both prime numbers. So that is the factorization of negative 525. Negative 1 times 3 times 5 times 5 times 7. Well, let's move down to this next example, because sometimes you're going to have variables involved. Well, it's going to work very much the same way. We're going to break down the 20 first. So 20 can be broken down into 2 times 10. And then the a can be broken down into a times a, because it's a squared. And then we have a b on the end. Well, we can factor this down one more time because 10 can be broken down into 2 times 5. And then the a's are still broken down, and so is the b. So now we have factored 20a squared b into 2 times 2 times 5 times a times b. By the way, as a side note, 2 is the only even prime number, which makes sense because every other even number can be divided by 2. So therefore, 2 is the only even prime number. It's the only even number that you should be using here. Every other number should be odd because all the other prime numbers are odd. So, how can we use this? Well, 2 or more numbers may have some common factors, okay? So, let's look at the prime factorization of 90. That would be 2 times 3 times 3 times 5. And the prime factorization of 105, 3 times 5 times 7. Well, we want to see what both 90 and 105 have in common. Well, they both have a 3, and they both have a 5. So since they both have a 3 and they both have a 5, we can multiply 3 and 5 together and get 15 and find that the largest number that will go into 90 and into 105 is 15. That is called our greatest common factor. And you'll often see it abbreviated as GCF. And here below, I have just provided the definition for the greatest common factor, your GCF. The greatest common factor of 2 or more integers is the product of the prime factors common to the integers. Okay, so in this example, 90 and 105 had 3 and 5 in common. You multiply 3 and 5 together, you get 15, and 15 is the greatest common factor of those two numbers. So let's move on to some examples of greatest common factor. And I'm going to break these down a little bit. So let's find the greatest common factor of 54, 63, and 108. Well, I'm not going to go through the entire exercise of breaking it down piece by piece. So I'm going to go ahead and give you what the prime factorization is of each of these. 54 is 2 times 3 times 3 times 3. 63 is 3 times 3 times 7. And 108 is 2 times 2 times 3 times 3 times 5. We want to find what all three of these have in common. Well, we've got a 3 here, a 3 here, and a 3 here. And as it turns out, we've got another 3 here, here, and here. And that's everything that all three numbers have in common. So, therefore, we can say that the GCF is 3 times 3, which would be 9. For example 20, let's break down these two. And now we're throwing in some variables. We've got 8a squared b, and we've got 18a squared b squared c. Well, 8a squared b can be broken down into 2 times 2 times 2 times a times b. And then 18a squared b squared c can be broken down as 2 times 3 times 3 times a times a times b times b times c. Okay, now let's find what they have in common. Well, we've got a 2 in common, and that's it for the numbers, because we have 2 2s and 2 3s. There's nothing in common there. We do have an a in common, we've got another a in common, and we have a b in common. So we take everything that we have in common, and we multiply it together, and we get our GCF as 2a squared b. Now, the reason we've gone through this is because you're going to use the greatest common factor when factoring using the distributive property. Okay? So let's look at example 21. Let's use the distributive property to factor 10y squared plus 15y. So first we need to find the greatest common factor. And for these numbers are simple enough that you should be able to break them down almost immediately. Because 10 is 2 times 5, both of those are prime numbers. And then you have y times y. 15 is 3 times 5, both of those are prime numbers. And then you have a y. Well, what do we share? We share a 5 and we share a y. So we can express the terms in that polynomial by using our GCF, which is 5y. Okay, so we have 10y squared plus 15y. This is going to equal 5y in the first term. Well, if we take 5y out, what's left? Well, we've got a 2 and we've got a y. And you can do a quick check because 5y times 2y equals 10y squared. So you can always do a quick check to make sure that you pulled everything out correctly. And then we have 5y. If we pull 5y out of the second term, the y is pulled out completely. And when we pull 5 out of 15, we end up with 3 left. And then we finally write our answer as 5y times 2y plus 3. We just factor out our 5y term. Okay, let's move on to example 22. Let's factor 6x cubed y plus 14x squared y plus 2x squared. Now when we do that, this is what we're going to find. So we have x to the third y. We have 14x squared y. And then we have 2x squared. And we're going to find out what our common factor is, what our greatest common factor is. And we do that by breaking it down. So 6 is 2 times 3. Both of those are already prime. Then we have times x times x times x times y. Then we have 14, which is 2 times 7. Both of those are already prime. Then we have x times x times y. And then we have 2 times x times x. Now this whole exercise I'm going through here of breaking everything down, you're going to get to the point where you don't need to do this. And in fact, if you're already at that point, then that's great. I'm just showing you what the process is. This is a process that you can very well do mentally when you're trying to find what the greatest common factor is. 6, 14, and 2 are all even, so obviously 2 is something that's going to be pulled out of all 3 of those, right? And we can't pull anything more than that out because 2 is the smallest of our 3 coefficients. Okay? When you look at x squared, and x to the third, well, obviously, we're only going to be able to pull 2 of those x's out. So we're going to be left with 1 in that first term. So we're pulling 2 x's out of each of these, and that leaves that 1x by itself on that first term. You're going to start to recognize these things. So our problem was 6x to the third y plus 14x squared y plus 2x squared. So our greatest common factor, is 2x squared. So that's what we're going to pull out. So we've got 2x squared times what's left in this first term. Well, we've got 3xy. And then we've got 2x squared coming out of the second term. What's left is 7y. And then when we pull 2x squared out of the third term, well, all that's left is 1, because 1 times 2x squared is 2x squared. And then we're going to pull 2x squared out in the front, and we're left with a polynomial on the end here. And that's it. We have factored that original polynomial. All right, now let's talk about factoring trinomials. Okay, you may recall the FOIL method for multiplying binomials. Okay, we went over that not long ago. So if we have 5x plus 2 times 3x plus 7, and we were to do the FOIL method on this, we would end up with the first two terms multiplied together, which would be 15x squared. And then the outside terms, so you've got 35x. And then your inside terms would give you 6x. And then your last terms would give you 14. And then we just simply add those middle two terms together. So when we do that, we end up with 41x in the middle. Okay, well, the binomials 5x plus 2 and 3x plus 7 are the factors of 15x squared plus 41x plus 14. Okay? So here's something to notice, because we're always looking for relationships, and we're always looking for where we have something that is a pattern in math. Math, again, is all about patterns. Well, you'll notice that 15 times 14 is 210. But you'll also notice that 35 times 6 is also 210. Okay, so we're going to use this information to reverse the process to factor trinomials. Okay, so we're going to do that with this next one, 2y squared plus 7y plus 6. Okay, so we know that the product of 2 and 6 is 12. So we need is two integers whose product is 12 and whose sum is 7. Okay, because we're going to add those two middle terms together to get 7. So basically what we're trying to do is, you know how we ended up with two of those middle terms that got put together? Now we're figuring out how we break those two middle terms apart. So we can use guess and check, because 12 does not have that many factors. So the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. Okay? Well, let's see what the sum of those factors are. So the sum of 1 and 12 is 13. The sum of 2 and 6, well, that's 8. And then the sum of 3 and 4 gives us 7. Well, we want one that gives us the sum of 7, right? So the first one doesn't work, the second one doesn't work, but the third one does. Okay? So we're going to select 3 and 4 as our factors. And when we do that, we're going to end up breaking our middle term apart. So you've got 2y squared in the front, that doesn't change, but we're going to break it down to 3 plus 4y. We're breaking down that middle term into a sum. So 3 plus 4 is 7, so we haven't changed anything about this trinomial. All we've changed is how it looks. Okay? And then we're going to break that apart. We'll distribute out to the y. So we've got plus 3y, plus 4y, plus 6. Then we're going to group the terms. So we're going to group the first two terms and the second two terms. And we're going to factor the first two, and then we'll factor the second two, which is called factoring by grouping. Okay? So let me write that step where we group these things, just so you can clearly see what's happening. We're grouping these terms together. Okay, so now we're going to factor the first terms. And when we do, we can factor a y out. So we're left with 2y plus 3 on the inside. Okay, now let's factor something out of these two terms. Well, we can factor a 2 out. That's our greatest common factor between 4y and 6. And that leaves us with 2y plus 3. Well, you'll notice that we ended up with 2y plus 3 terms in the front and on the back. So therefore, we can break this down into y plus 2, which are our outside parts, and then the part that was in common, which was 2y plus 3. And we have now successfully factored 2y squared plus 7y plus 6. And y plus 2 and 2y plus 3 would be those factors. So let's do another example of this. Let's find the factorization of 5x squared minus 17x plus 14. Well, when we do this, we want to multiply 5 and 14. When we do, we get 70. So we're looking for the factors of 70 that add to give us negative 17. Okay? So, since we're looking for some factors of 70, and we know we're going to end up getting something times something as a positive number, but the middle number being negative, then we know that both of our terms, to get a factor of 70, both of those have to be negative, because a negative times a negative is a positive. And we're looking for our factor, we're looking for something that's a product of a positive number, but that will add to give us something negative. So the only way we can do that is if it's multiplied to give us positive through two negative numbers, so that the two negative numbers will add to give us a negative number. Okay, so let's list our factors of 70. So we've got negative 1 and negative 70, okay, because negative 1 times negative 70 is 70. We've got negative 2 and negative 35. Will 3 go into it? No. Will 4 go into 70? No. 5 will. Got negative 5 and negative 14. And then we've got negative 7 and negative 10. Those are our factors. Okay? Now, let's do the sums. Negative 1 plus negative 70 gives us negative 71. Well, that's not negative 17, so that one's not going to work. Negative 2 plus negative 35 gives us negative 37. Well, that's not negative 17, so that won't work. Negative 5 plus negative 19, or I should say negative 14, getting ahead of myself. That's going to be negative 19. So that's not negative 17. We're getting closer, but that's not negative 17, so that won't work. And then negative 7 plus negative 10, that is indeed negative 17. So that's what we're going to use. We'll use negative 7 and negative 10. So let's just come over here and let's factor it. So we've got 5x squared. Now we're going to use negative 7 and negative 10 in place of negative 17. So we've got plus negative 10 plus negative 7, and all of that's going to be in front of our x, plus 14. Now we've got 5x squared minus 10x minus 7x plus 14. And now we're going to factor by grouping. Okay? So when we factor by grouping, we're going to end up with x coming out, but we can also pull out a 5. So we end up with 5x. What's left is an x in the first term and a 2 in the second term. And we're going to factor out in the first one. We'll factor a 2 out. Or I should say a -7. Okay? We're going to factor a -7 out because -7 will go into both -7 and 14. And then we're left with x because -7 times x is -7x. And we're left with a -2. -2 times -7 is positive 14. And then we break apart our pieces. 5x minus 7 times x minus 2. And now we have factored that original polynomial. And you can do a quick check on this by multiplying these two binomials using the FOIL method. That should get you back to the original polynomial in the problem. All right, so now when the leading coefficient is 1, it actually makes the problem a little bit easier. There's no need to split the middle term. You can simply use the factors as your two constant terms in the result. Okay, so here in example 24, our leading coefficient is 1. We just have an x squared. There's no number in front of it. So let's find our factors of -6. Okay, so here we're finding two numbers that are going to multiply to give us -6. So to multiply to give us -6, one number has to be positive, the other has to be negative. So if we look at it this way, we have two numbers that have to be positive, or one number has to be positive, one has to be negative. Well, they have to add to give us a positive number, okay, because we have positive 5 as our middle term, positive 5x. Well, the positive term in the middle tells us that the bigger number is going to be our positive number, and the smaller number will be our negative number. Okay? So let's first of all look at what the factors of 6 are. Okay? We have 1 and 6, and we have 2 and 3. Okay? Well, the middle number being positive tells us the bigger number is going to be the positive number, which means our smaller number has to be negative. Okay, now we're going to look at these factors and see which one adds up to give us 5. Well, we have it right off the bat. We have -1 plus 6 equals 5, and there it is. We don't have to even go on to the other factors. Okay? Now, if you wanted to, you could, just to verify, -2 plus 3 is 1, and that obviously doesn't work. So there we are, -1 and 6. When that is the factorization that we're going to use, since we have a leading coefficient, you don't have to split up the middle term. You can just simply say x minus 1 times x plus 6. And that would be your answer. Okay, so this is the easiest trinomial to factor because you don't have to worry about breaking down that middle term. Okay, now let's talk about factoring differences of squares. Okay, this is just another type of thing that you're going to run into, and this one really is not that difficult. Okay, it's all about recognition. Okay, so a polynomial is a difference of squares if there are two terms, one subtracted from the other. That's where the word difference comes from in the title. And both of the terms are perfect squares. That's where the squares comes from, okay? So let's look at this. 4x squared minus 9. This would be considered a perfect square because we have 4x squared, which can be broken down to 2x times 2x, so it's 2x squared, quantity squared. And then we have 9, which can be broken down to 3 times 3, and they're a difference. So therefore, 4x squared minus 9 would be a difference of squares. And here's the definition for you. This is the definition of the difference of squares. A squared minus b squared equals a minus b times a plus b, or you can write it the other way around. It doesn't really matter. Okay, so these examples will go fairly quick. Let's factor a squared minus 64. Well, a squared is a square. 64 is a square because it's the square of 8. So we can say that this is a squared, and we can say that this is 8 squared. So therefore, we can write the answer as a minus 8 times a plus 8. If you want to write it the other way around, you can. You can say a plus 8 times a minus 8. And that's it. That's your answer. So the first step is just recognizing that you have a square as your first term and a square as your second. All right, let's look at the second example here, example 26. Let's factor 9x squared minus 100y squared. Well, we do have a difference of squares again, because 9x squared is 3x quantity squared, and 100y squared is just 10y quantity squared. Okay, so therefore we can just write this as 3x minus 10y times 3x plus 10y. And that's it. That's your answer. Now, you may not have something that's a difference of squares right off the bat. You may have something that you have to factor out first. So that's the case here in example 27. In example 27, you need to factor out a greatest common factor first. Well, what's the biggest number that can go in to 12 and 27? Well, that would be 3. Okay, so 3 is the greatest common factor there. This term has an x cubed to the cubed, x cubed. This one has just an x, so you can pull out an x as well. So our greatest common factor is a 3x, and then you're left with 4x squared minus 9y squared. Well, now we have a difference of squares. 4x squared is a square, and 9y squared is a square. So therefore, that can be broken down into their square roots, which would be 2x minus 3y times 2x plus 3y. And so this would be your final answer. Now the last thing I want to cover in this section is factoring perfect square trinomials. So you may remember early on in this video, I brought out the term perfect square trinomials. It was one of our examples of a trinomial. Well, here's what we're talking about when we're talking about perfect square trinomial. Numbers such as 1, 4, 9, 16, they are all called perfect squares. And they're called perfect squares because they can be expressed as a square of an integer. Now, products of the form a plus b quantity squared and a minus b quantity squared are also called perfect squares, and the expansion of these products, those are called perfect square trinomials. Okay, and here we have what they look like. These are perfect square trinomials. Okay, so we basically have a plus b quantity squared can be written as a squared plus 2ab plus b squared. A minus b quantity squared can be written as a squared minus 2ab plus b squared. So what you have on the right hand side is the problem that you would be presented, and if you can recognize that as being a perfect square trinomial, then you can factor it into what is on the left hand side. So as always, the best way to do this is go through a few steps, and we'll go through a couple of examples. So here's how you determine if what you have is a perfect square trinomial. First, is the first term a perfect square? Okay, if you can say yes to that, move on to the second question. Is the last term a perfect square? If you can say yes to that, then the final question, is the middle term twice the product of the square root of the first and the last? Now that one sounds a little heavy duty, but don't worry, I'm going to show you what it means when we do these examples, okay? You don't even have to get to that third question if you answer no to 1 or 2, okay? So let's go to example 28. Let's determine if x squared plus 22x plus 121 is a perfect square trinomial. Okay, and if so, we will factor it. All right, well, first of all, is the first term a perfect square? Well, x squared is x squared. I know it sounds a little funny to say it that way, but the variable x, if you square it, you get x squared. So yes, it is a perfect square. So here we can say yes. All right, is the last term a perfect square? Well, do you remember your times tables? Well, you might recognize 121 as being 11 squared. Okay, so then yes, we can say yes to that. The last term is a perfect square because it's 11 squared. All right, so now, this is what the third question really means. Is the middle term twice the product of x and 11? Okay, so if we take x and 11, okay, we make it x times 11, and if we double it, we multiply it by 2, what do we get? Well, we get 22x. Is that our middle term? Yes, it is. So therefore, we have a perfect square trinomial. And our perfect square trinomial can be factored as x plus 11 squared. And the reason we use plus in here is because all of these values, all the operations are plus. And it's more specifically, the first operation is plus. Okay, it's that first operation that you really want to look at. The second operation should always be plus when we're doing these. So it's the first one that you want to look at. All right, let's do a couple more of these. Example 29. Let's determine if 16a squared minus 72a plus 81 is a perfect square trinomial. Well, is the first term a perfect square? Well, 16a squared is 4a quantity squared. So yes, the first term is a perfect square. Is the last term a perfect square? Well, 81 is just 9 squared, right? So since 81 is 9 squared, we can say yes to this one. And then finally, is the middle term twice the product of 4a and 9? Okay, so we've got 2 times 4a times 9. And what is that product? Well, that product is 2 times 4 is 8. 8 times 9 is 72. And then you've got an a in there. So yes, the middle term is 72a. So you can say yes to that last one. And so we can factor this. You'll notice that the second sign, or the first operation, I should say, is negative. Since that first operation is negative, then we are going to subtract our 2 squares, our 2 square roots. So we've got 4a minus 9 squared. And that is the factorization of the original polynomial. All right, let's do one last example to wrap up this section. Example 30. Determine whether 9p squared minus 56p plus 49 is a perfect square trinomial. And if so, let's factor it. Okay, so first of all, is the first term a perfect square? 9p squared is simply 3p quantity squared. So yes, it is a perfect square. This last term, 49, well, if you know your square roots, 49 is 7 squared. So yes to that one as well. Is the middle term twice the product of 3p and 7? Well, 2 times 3p times 7. What does that give us? Well, 2 times 3 is 6. 6 times 7 is 42. And then you got your p here. Well, 42 is not the same as 56. So therefore, no to that third question. So therefore, we can say 9p squared minus 56p plus 49 is not a perfect square trinomial. And that would be our answer to that, at least in terms of what they're asking. They're asking if it was a perfect square trinomial. If so, factor it. Well, since it's not, there's nothing to factor. So that would be our answer. And this wraps up our Section 4 notes for Unit 0. This also wraps up the unit. So the next video that will come out will be the first section of Unit 1.